Welch's t-test is a way of building confidence intervals and doing hypothesis testing when you're thinking about the difference between population means, between two populations. So let's set up the problem. We have two random samples. The first random sample is of size n1, and it's from a normal population with mean mu1 and variance sigma 1 squared. The second random sample is of size n2, which is not necessarily the size as the first random sample. And the second random sample is from a population with normal mean mu2 and variance sigma 2 squared. We know that the distribution of the sample mean is follows a normal distribution with mean mu1 and variance sigma 1 squared over n1. The distribution of x1 bar minus x2 bar is equal to, or follows a normal distribution with mean mu1 minus mu2 and variance equal to the sum of the variances of each sample mean. That's because the two random samples are independent from one another. Here we standardize and we subtract the mean and divide by the standard deviation, and we get a standard normal. Now, this random variable here would normally allow us to build confidence intervals and do hypothesis testing, but the only problem is often we don't know the population variances for population 1 and 2, and that really hampers our ability to use this. So we need to come up with estimates of the population variances. Alright, so we don't know the population variances, so we have to create an estimate, S1 squared, the sample variance for population 1, and that's shown right here. Now we know from a theorem that S1 squared, the sample variance, if you standardize it by multiplying by this, you get a chi-squared distribution with n1 minus 1 degrees of freedom, right? But our standard error for the difference between sample means, this is our standard error, right? This whole part here. And so if we need to come up with a distribution for the standard error, and one way of approximating the standard error is to use SD squared, which is just the standard deviation, or this sample variance for population 1 divided by n1 plus sample variance for population 2 divided by n2. And if we can find the distribution of SD squared, and then we will be able to use a statistic of this sort of form, except using SD squared in the denominator, using the square root of SD squared in the denominator, then we're going to be able to do a t-test. And that's because SD squared, we're going to find that it follows a scaled chi-squared distribution, which makes sense because the sample variances also follow scaled chi-squared distributions. So there's some, probably does too. Here's some quick facts about moment-generating functions. Here's the definition of a moment-generating function. Here's the property of, if you take derivatives of the moment-generating function and evaluate them at t equals 0, you get various moments of the random variable. And here's some extra properties. So if a and b are constants, then the random variable defined by x plus a is just e to the at times moment generating function of x. Moment generating function of b times x is just equal to the moment generating function of x evaluated at bt. And if x and y are independent random variables, then moment generating function defined by x plus y is just equal to the product of the two moment generating functions. That's going to be important later. Now let's talk about scaled chi-squared distributions. So let W be a chi-squared distribution with v degrees of freedom. Let's let A be a scaled chi-squared distribution defined by little a times W, where little a is just a constant. Then we can find the moment generating function of big A by using the rules of moment generating functions with multiplying by a constant. And we also know the moment generating function of a chi-squared distribution. And so if we just plug in AT into a chi-squared distribution with v degrees of freedom, we get this moment generating function here. And now that equips us to be able to find the expected value of A in terms of the scaling factor little a and the degrees of freedom v, and it also allows us to find the expected value of a squared, and that's this right here. Okay, so given any scaled chi-squared distribution, I can tell you what the expected value is and the second moment. All right, now comes the time when we're going to try to approximate SD squared, which is our estimate of the square of the standard error. We're going to try to approximate SD squared with a scaled chi-squared distribution. And remember, our scaled chi-squared distribution was just A. And so we're going to equate the expected value of SD squared with the expected value of A. And the same for the second moment. And hopefully that will give us a good fit for our SD squared. All right, so we're going to say that C1, define C1 to be this scaled version of our sample variance for population 1. And we know that this follows a chi-squared distribution, so that the moment generating function of C1 is just the moment generating function of a chi-squared distribution with n1 minus 1 degrees of freedom. Now, the moment generating function of S1 squared, the sample 1 variance, divided by n1, well, that's just this constant right here times C1, because the sigma 1 squared cancels with the sigma 1 squared in the denominator here. The n1 minus 1 cancels with the n1 minus 1 over here, and you divide by n1, and that gives us the sample variance divided by n1. And so using our multiplying by constants rule with moment generating functions again, we can find the moment generating function of s1 squared divided by n1. Okay, now that we have that, we can find the moment generating function of SD squared, right? SD squared is just S1 squared over N1 plus S2 squared over N2, right? And since S1 squared and S2 squared are independent from one another, we know that the moment generating function of their sum is just the product of each of their moment generating functions. We already know their moment generating functions. And so we get finally that the moment generating function of SD squared, our estimate of the standard error squared, is just equal to this. And this function here, which is the product of two functions, can be easily differentiated once and evaluated at 0 to get the expected value of SD squared, and it can also be differentiated twice, evaluated at 0 to get the second moment of SD squared. And we find that the expected value of SD squared is sigma 1 squared over n1 plus sigma 2 squared over n2, which makes sense because we want SD squared to be an unbiased estimator of the square of the standard error. Alright, so we also have the second moment of SD squared here. Now it's time to equate our generic scaled chi-squared distribution with SD squared, and then find out what degrees of freedom and what scaling factor we're going to need in order to get SD squared to be approximately equal to a chi-squared, to a scaled chi-squared. So here we're just setting the expected value of A, which is little a times V. We're setting that equal to the expected value of SD squared, which is just the standard error squared, which means that the scaling factor is just the expected value of SD squared divided by V, the degrees of freedom. If we do the same thing with the second moments, equating the second moment of A squared, equating the expected value of A squared to the expected value of SD squared, then what we get, we can substitute in for A in this equation, and finally we can solve for V, the degrees of freedom. Now what's interesting here is, so we get that V equals 2 times the expected value of SD squared, the quantity, squared, divided by the expected value of SD squared, the SD squared, so that's the second moment of SD squared, and minus the expected value of SD squared, the quantity squared. And so if you notice, the denominator here is actually the variance of SD squared, right? So now we have our degrees of freedom and our scaling factor, little a. All that's left is to build our t-test. So first of all, just recall that this random variable that I wrote here is just a standard normal, right? Also recall our definition of A. A is a scaled chi-squared distribution. A divided by little a equals W, which is just a chi-squared with V degrees of freedom. Also recall that V, the degrees of freedom, times A, the scaling factor, is equal to the square of the standard error, sigma 1 squared over n1 plus sigma 2 squared over n2. Finally, we can write this and use a theorem from our textbook that if you take a standard normal random variable, you divide it by the square root of the quantity chi-squared random variable divided by the degrees of freedom of that chi-squared random variable, you get a t distribution with V degrees of freedom. Alright, and we can simplify this denominator here, A times V. Well, A times V, we already said V times A equals the square of the standard error. The square of the standard error, take the square root of that, right? And that cancels with the standard error in the numerator, in this part, this top part. So this cancels out with these two. And we're just left with the difference of the sample means minus the difference of the population means divided by the square root of big A. And now we can recall that the whole process of what we just did was to fit SD squared to be approximately the same distribution as A. So now we just replace A with SD squared, and we still have a t distribution with V degrees of freedom. And finally, let's just show that this is our formula for V from the previous page. This was the expected value of st squared, the quantity squared, and then this denominator was the variance of st squared. It's important to note that v may not be a whole number, as is typical, but this doesn't usually cause very many problems. Okay, so the only issue with what we just did was that our estimate of v, the degrees of freedom, relies on sigma 1 squared and sigma 2 squared. And those were the quantities which we didn't know in the first place, which is why we had to do this whole thing. So what we're going to have to do is replace sigma 1 squared with s1 squared, the sample variance, and likewise with population 2. And so we'll get this new estimate of v. Okay, and this is the estimate of v that we're actually going to use when we are doing our t-test, like if we're finding a t-value. All right, one more thing. I want to show you guys some R code that I wrote to show that the standard error is approximated very well by this quantity here, which is s1 squared over n1 plus s2 squared over n2, all in square root. Now, there's also another way of approximating the standard error. This is the real standard error which we're trying to approximate. But this method, which is called the pooled variance method, is another way of approximating the standard error. And I just wanted to show you that the way that I explained with Welch's t-test is a really good way.